Oh, hello everyone. Today in this video we will talk about the goodness of fit tests, which is the last topic in confidence intervals and hypothesis testing in chapters, let's say 8, 9, and 10. So this is the last topic of these three chapters. So goodness of fit test, well, it is used to determine if a population has a specified theoretical distribution. So up to now, we talk about whether the population has a specified mu or not, whether it has a specified sigma or not, whether it has a specified p proportion or not. But now we will discuss whether a population has a specified theoretical distribution or not. Okay? So we need to have a random sample from that population, and the test is based on how good a fit we have between the frequency of occurrence of observations in the sample and the expected frequencies. Okay. So what we have is, again, we just look at the expected frequencies, okay, and the, let's say, the theoretical frequencies. Okay. So this is just like uh, the when we are just making a hypothesis, we just check whether mu and x bar, whether they are close enough to each other or not. If they are close enough, we say that, okay, I cannot reject the hypothesis. So similarly, I just look at the expected frequencies and then I just check the theoretical frequency. So in fact, this is just vice versa. So this is mu theoretical expected, or what we observe is x bar. So if they are close enough to each other, then we don't reject the hypothesis. Okay? So suppose, as a first example, a gambler wishes to see if a given die is balanced or not. Okay? So we are just working on a die. Remember what a die is, right? This is something like this. So I have just like one here. So I don't know, two here, and I have, for example, four here, right? So what they do is they just throw the die, okay, 120 times and count the frequency of occurrence of each phase value. Okay? Each phase value to obtain a sample distribution as follows. So as you see, this is the observed value for one. What does it mean? It means that you just throw it 120 many times and uh, you observe one in 20 of these experiments. Okay? And you observe two in 22 of these experiments. You observe three in 17 of these experiments, and so on and so forth. Okay? So these are the observed values. These are the observed values. The first row is the observed values. How about the second row? Second row is the expected number of occurrences, right? So how do we find this? How do we know that we expect to see 20 many ones, 20 many twos, 20 many threes? How do we know that? Well, that's simple. The probability that you observe one, that's equal to 1 over 6, right? Because you have a die. If it's a balanced die, right? If it is a balanced die, if it is a unbiased die, then the probability that you observe 1 is equal to 1 over 6, which is also equal to probability that x is equal to 2. That's also equal to probability that x is equal to 3, and so on and so on. Okay, so all of the probabilities are equal to each other, and that probability is equal to 1 over 6. Okay, so remember what we talk about the probabilities. For the probabilities, we say that, well, for a single observation, it just shows the probability of observing that amount, and in terms of the population, it just shows the percentage, right? The percentage of the occurrences. So here, this means that 1 over 6 times of your observations, you will observe one. 1 over 6 times of, let's say, 1 over 6 of your observations, you will observe two. And 1 over 6 of your observations, you observe three, and so on and so forth. So how do we get 20? So this is the total number of observations that you have times the probability of 1 over 6. That's equal to 20, right? So um, what you expect is to see on the average too many ones, and similarly just look at here 120 times 1 over 6. You expect to observe 20 many twos, okay, and so on and so forth. So this is how to calculate the expected frequencies, okay? That's the probability times the number of observations that you have, right? P times N. Don't forget this because we will use later in the other questions as well. So the balanced time means all phases have the same probability of occurrence, right? All of them has the same probability, which is 1 over 6. Okay. So what is our H0? H0 is the sample data come from the specified distribution. What is the specified distribution? The specified distribution, well, says that the die is balanced, which is probability that x is equal to x is equal to 1 over 6 for small x equal to 1 to dot 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 6. Okay. For all of the values of x from 1 to 6, the probability that x is equal to x is just 1 over 6. And H1, the alternative one, the sample data do not come from the specified distribution. What does it mean? Well, there is a problem with the die. The die is not balanced. Okay. So this is my H0. The sample data comes from the specified distribution, which is 1 over 6 for every observation. Okay. And H1, the sample data do not come from the specified distribution. Okay? So in fact, this is my step 1, right? Just write your hypothesis. Step 2, well, choose your test statistic. What is the test statistic? Well, it turns out that the scientists have shown you can just use a chi-square random variable for this, for testing this hypothesis. Okay? But how do we calculate chi-square observed? It turns out that this summation, what is this summation? We will see this in a minute, is chi-square distributed. So what is this distribution? It is the observed I minus the expected I squared divided by the expected I. So what does it mean? Observed I minus expected I. Just go back. So let me just write it here. The chi-square random variable is equal to just sum observed I minus the expected I squared divided by the expected I. So the observed I, for example, for the first one, okay, let me just erase this. Sorry, just erase all of them. Let me see if I just, okay, I cannot undo it. Okay, let me just write it again. So it was OI minus expected I squared divided by expected I. So what is O1? The observed value for the first observation. O1 is this, right? What is E1? E1 is the expected observation for the first experiment, which is this. So this is OI, this is O1, right? This is E1. So O1 minus E1, that's equal to 0, right? Divided by E1, which is 20. So 0 divided by 0 squared divided by 20, that's equal to 0. So what is O2 here? O2 is 22. This is the observed frequency of the second experiment for the value where you just want to observe 2. Okay. And what is E2? E2 is equal to 20. So the difference between them is 2. 2 squared divided by EI, which is 20. Right. So what you do is you just take the difference, square it, and then divide it by the expected value, which is 20 in this example. Okay. Okay. So step 3, well, what is your critical region? So the critical, in order to find the critical region, let me just again plot the chi-square random variable. So remember, it was not a symmetric one. It starts at 0, right? And it is skewed to the left. So this is my chi-square random variable. So just look at this chi-square random variable, okay? So let's try to see where is our let's say critical region. Should it be here or here or at both? Okay, let's try to see this. So in order to understand this, what I do generally is that let's try to see, for example, what happens if OI is equal to EI. So what does it mean? Just go back. Let's go back. So this is my OI. Okay, so the first subset is the first row, sorry, is the OI, and the second row is the EI, okay, the expected value. So if OI is equal to EI, what does it mean? So you will have something like this: 20, you will observe 20 for the first die, 20 for the second experiment, 20 for the third. So this is 1, 2, 3, 4, 5, 6. 24, you will observe too many many fours, you will observe too many fives, you will observe too many six, right? And this is your observation. If this is your observation, right, is there any evidence which makes you suspect that your die is not balanced, or which makes you suspect that your H0 is not correct? Well, there is no evidence, right? Because you exactly see the expected values here. So what does this mean? So if you just observe a perfect die in your experiments, then your chi-square value will be equal to 0, okay? If you have a perfect experiment result, right? Okay. So what does this mean? This means that, well, this region is not a critical region, okay? But so if OI is very different than EI, what does it mean? So if OI, let me just change my color here. So if OI is strictly different than that, what does it mean? So for example, if you just observe 80 many ones, okay, 5 many twos, too many threes, okay, 3 many fours, 25 many fives, right? And 5 many six. So then, if these are the observed values, if you just take the difference between the expected one, which is 2020, 2020, let me just write it there. So if you just take the difference, what you see is 60 squared divided by 20, okay? So this is 15 squared divided by 20, and this will be a very large value, okay, very large. So if you just observe a die like this, what does it mean? It means that, well, this is a problematic die, okay? So this is in fact, an unbalanced die, right? Unbalanced die. So what does this mean? If chi-square is strictly greater than 0, if it is very, very large than 0, then you have a problematic die, okay? You have an unbalanced die, right? So what does this mean? Your critical region is somewhere here. Okay, so what you do is you just put your alpha here, and this is your chi-square, which is an area of alpha here. So your critical region is, or rejection region is, chi-square alpha, okay, infinity, right? So just look at here, chi-square, observe if it is greater than chi-square alpha. So how many degrees of freedom? Well, you will have k minus 1 degrees of freedom. So in our example, k is equal to 6, k minus 1, that's equal to 5 degrees of freedom. If it is greater than this, okay, so let me just write step 4. Step 4, just calculate what? Calculate chi-square observed, okay, chi-square observed. And in step 5, just check this decision rule, right? Just check this. If so, your chi-square observed is greater than chi-square alpha at k minus 1 degrees of freedom, then you will what? You will just reject your H0, okay? Okay, so if you just write the chi-square random variable, then it turns out that, well, the chi-square value is 1.7. Okay, if you just check the critical value of chi-square, which is the chi-square leaves an area of 0.01 at 5 degrees of freedom, okay? Sorry, at v is equal to 5 degrees of freedom. So this value is 15.016, okay? So if you just plot this, it's something like this. So this is my chi-square random variable. This is 15.068. And this area here is what? This is equal to 0.01. And what is my chi-square observed? chi-square observed is somewhere here. Okay, it's very, very close to, in fact, what? Close to 0 when you just compare it with the critical chi-square. So your chi-square is equal to 1.7. Okay, this is what you have. Hence, you do not reject H0. Okay, so what does it mean? What does it mean? If you don't reject H0, it means that, well, the die is balanced. So you don't have any evidence to suspect that, or the evidence that you have is not sufficient to suspect the H0, which says the die is balanced. Okay? So if you just calculate the p-value, what is the p-value? So this is the prob of the expression for a p-value. Okay, so please be careful with this. This is the prob of the expression. This is not x squared, but this is chi-square. Okay, so chi-square has something like this. It's like this. Okay, so you have a curved. So the one part of the cross of this x is a bit curved. Okay? So this is chi-squared greater than 1.7. So what is 1.7? Remember, this is chi-squared observed, right? So what we are trying to do in p-value? Remember, it's this area. Okay. So what is this area? It turns out that this area is equal to 0.89, which is a very, very large value which is a very large p-value. Remember what a p-value was. So p-value was the credibility of the null hypothesis. So the null hypothesis, the credibility of null hypothesis is very large, which means so you cannot reject the null hypothesis. Okay, and your conclusion is, so at the end, you don't reject the null hypothesis. What does this mean? It means that, well, the die seems to be balanced. Okay? So